What is ferrite core inductor? How does it function in its application? A ferrite core inductor is a type of inductor that uses a ferrite core to increase its inductance. Ferrite is a ceramic material made by mixing iron oxide, Fe₂O₃, with other metallic elements. Ferrite cores are used in inductors because of their high magnetic permeability and low electrical conductivity, which minimizes eddy currents and reduces energy losses at high frequencies. Ferrite core inductors function by utilizing a ferrite material as the core to enhance the magnetic properties of the inductor. The core plays a crucial role in increasing the inductance and improving the efficiency of the inductor, particularly at high frequencies. Here's a detailed breakdown of how ferrite core inductors function. Basic principle of induction: magnetic field creation. When an electric current flows through a coil of wire, it generates a magnetic field around the coil. The strength of this magnetic field is proportional to the amount of current flowing through the coil and the number of turns in the coil. Energy storage. The inductor stores energy in the magnetic field created by the current. When the current through the coil changes, the inductor opposes the change by inducing a voltage, according to Lenz's law, which allows it to release or absorb energy from the circuit. Role of the ferrite core. The ferrite core significantly enhances the performance of the inductor by improving its ability to store energy in the magnetic field. Here's how. Increased magnetic permeability. Ferrite materials have a much higher magnetic permeability than air or non-magnetic materials. This means that they can concentrate magnetic flux more effectively. When the coil is wound around a ferrite core, the magnetic flux generated by the current is concentrated within the core, leading to higher inductance. Reduction of eddy currents. Ferrite is a ceramic material with high electrical resistivity. This reduces the formation of eddy currents, circular currents induced in conductive materials by a changing magnetic field within the core. Eddy currents cause energy losses in the form of heat, especially at high frequencies. The high resistivity of ferrite minimizes these losses, making ferrite core inductors more efficient, particularly in high-frequency applications. Energy storage and release. The ferrite core enables the inductor to store more energy in the magnetic field for a given amount of current. When the current decreases, the energy stored in the magnetic field is released back into the circuit, helping to smooth out fluctuations in current or voltage. Frequency response. Ferrite core inductors are particularly effective at higher frequencies, ranging from kilohertz to megahertz. The core material is optimized to reduce losses at these frequencies, making these inductors ideal for radio frequency, RF, applications, power supplies, and EMI suppression. Core shapes and configurations. The geometry of the ferrite core also influences the performance of the inductor. Common shapes include toroidal cores. These are donut-shaped cores that provide a closed magnetic path, minimizing leakage of the magnetic field. E-cores and U-cores. These shapes are often used in transformers and power inductors to provide a balanced magnetic circuit. Ferrite beads. Small cylindrical ferrite cores used for EMI suppression on cables and circuit boards. Key factors in functionality. Inductance. The presence of the ferrite core increases the inductance value of the coil, allowing it to store more energy and effectively filter or block AC signals, particularly at higher frequencies. Efficiency. The reduction in eddy current losses due to the ferrite core's high resistivity enhances efficiency, especially in circuits that operate at high frequencies. Frequency handling. Ferrite core inductors are ideal for handling high-frequency signals, making them suitable for RF circuits and power electronics. In summary, ferrite core inductors function by using a ferrite material to enhance inductance, reduce energy losses, and improve the overall performance of the inductor, especially at high frequencies. Here's how it works. Electric current flow in an inductor is a fundamental aspect of how inductors operate. Here's a detailed look at how electric current flow affects an inductor. 1. Basic concept of current flow. Electric current. Electric current is the flow of electric charge through a conductor, such as a wire. In an inductor, this current flows through a coil of wire wound around a core material. Direction and magnitude. The direction of the current flow is determined by the voltage applied across the inductor, and the magnitude of the current depends on the resistance of the circuit and the applied voltage. 2. Magnetic field creation. Current and magnetic field. When an electric current flows through the coil of an inductor, it generates a magnetic field around the coil. According to Ampere's law, the magnetic field B created is proportional to the current I and the number of turns N in the coil. Right-hand rule. The direction of the magnetic field can be determined using the right-hand rule. If you curl the fingers of your right hand in the direction of the current flow around the coil, your thumb points in the direction of the magnetic field inside the coil. 3. Inductance and energy storage. Inductance. The ability of an inductor to store energy in its magnetic field is quantified by its inductance, measured in henries H. Inductance depends on factors like the number of turns in the coil, the core material, ferrite and ferrite core inductors, and the geometry of the coil. Energy storage. The magnetic field created by the current flowing through the inductor stores energy. The energy, E, stored in the magnetic field is given by the formula. Inductive reactance. Opposition to change. An inductor opposes changes in current flow due to its inductance. When the current through the inductor changes, the changing magnetic field induces a voltage, back electromotive force or EMF, in the opposite direction to oppose the change, according to Faraday's law of induction. Inductive reactance, X_L. This opposition is quantified as inductive reactance, which increases with frequency. 5. Transient response. Current changes. When the current through an inductor changes, such as when a circuit is turned on or off, the inductor resists the change in current. This resistance creates a transient response where the current gradually ramps up or down rather than changing abruptly. Time constant. Tau, the rate at which the current changes, is characterized by the time constant. Asterisk 6. AC and DC behavior. Direct current, DC, for a steady DC current. The inductor eventually reaches a state where it behaves like a short circuit, low resistance, as the magnetic field stabilizes and no voltage is induced. Alternating current, AC for AC. The inductor continuously opposes changes in current, causing it to exhibit inductive reactance, which affects the impedance of the circuit. In summary, electric current flow through an inductor creates a magnetic field, which stores energy and affects the circuit's behavior. The inductor opposes changes in current due to its inductive properties, influencing both DC and AC circuits in different ways. Magnetic flux concentration in an inductor, particularly one with a ferrite core, is a key factor in enhancing the inductor's performance. Here's how it works and why it's important. 1. Magnetic flux basics. Magnetic flux. Phi magnetic flux is a measure of the total magnetic field passing through a given area. It is calculated as the product of the magnetic field, B, and the area, A, through which the field lines pass. Phi equals BA, where B is the magnetic flux density and A is the area perpendicular to the magnetic field. 2. Role of the core. Core material. The core of an inductor, particularly when made of ferrite, plays a crucial role in concentrating magnetic flux. Ferrite is a material with high magnetic permeability, which enhances its ability to channel and focus the magnetic field lines generated by the current flowing through the coil. Magnetic permeability. Magnetic permeability is a measure of how easily a material can become magnetized and how well it conducts the magnetic field. Ferrite cores have high permeability, allowing them to concentrate magnetic flux more effectively than air or other non-magnetic materials. 3. Effect of ferrite core on magnetic flux. Increased flux density. By placing a ferrite core inside the coil, the magnetic field lines are concentrated within the core material rather than spreading out into the surrounding air. This increases the magnetic flux density within the core. Enhanced inductance. The increased flux density results in higher inductance for the coil. Inductance, L, is proportional to the magnetic flux linkage per unit of current. The core's high permeability allows the coil to link more flux for a given current, enhancing the inductor's ability to store energy. 4. Magnetic flux path. Closed magnetic path. Ferrite cores typically have shapes that provide a closed magnetic path, e.g., toroidal or E-shaped cores. This design reduces the leakage of the magnetic flux and ensures that most of the flux remains within the core material, further increasing efficiency. Reduction of flux leakage. By concentrating the magnetic flux within the core, the ferrite material minimizes flux leakage, which helps to improve the coupling between the coil windings and enhances the inductor's performance. 5. Impact on inductor performance. Higher efficiency. Concentrating the magnetic flux within the ferrite core reduces energy losses associated with flux leakage and eddy currents. This results in a more efficient inductor, especially in high-frequency applications. Better energy storage. With increased inductance due to higher magnetic flux concentration, the inductor can store more energy in its magnetic field, which is crucial for applications like power supplies and RF circuits. Improved filtering. In applications where inductors are used for filtering, the ability to concentrate magnetic flux enhances the inductor's effectiveness in blocking unwanted frequencies and smoothing voltage fluctuations. 6. Applications and design considerations. Design optimization. Engineers design inductors with specific core shapes and materials to optimize magnetic flux concentration for particular applications. For example, toroidal cores are used to create a closed magnetic path and reduce external magnetic interference. Frequency handling. Ferrite cores are particularly effective at high frequencies, where they help in minimizing losses and improving performance in RF and switching power supply applications. In summary, magnetic flux concentration is crucial in enhancing the performance of inductors. Ferrite cores improve this concentration by providing a high permeability path for the magnetic field, leading to higher inductance, better efficiency, and improved performance in various electronic applications. Energy storage in an inductor involves storing energy in the form of a magnetic field when current flows through it. This principle is central to the operation of inductors and is a key aspect of many electronic and electrical systems. Here's a detailed explanation of how energy storage works in an inductor. 1. Basic concept of energy storage. Magnetic field creation. When an electric current flows through the coil of an inductor, it generates a magnetic field around the coil. This magnetic field represents the stored energy. Energy storage formula. The amount of energy, E, stored in an inductor. 2. How energy is stored. Inductance. L. The inductance of an inductor determines how effectively it can store energy. Inductance is influenced by factors such as the number of turns in the coil, the core material, e.g., ferrite, and the geometry of the coil. Current and magnetic field. As current flows through the inductor, the magnetic field builds up around the coil. The energy is stored in this magnetic field. The stronger the current and the higher the inductance, the more energy can be stored. 3. Behavior during current changes. Increasing current. When the current through an inductor is increasing, the magnetic field around it strengthens. The inductor stores energy in this growing magnetic field. The rate at which the energy is stored depends on the rate of change of the current. Decreasing current. When the current through the inductor decreases, the magnetic field collapses. The inductor releases the stored energy back into the circuit. This release occurs as the inductor generates a voltage, back EMF, that opposes the reduction in current, trying to maintain the flow of energy. 4. Transient response. Time constant. Tau, the time constant of an inductor, is a measure of how quickly it responds to changes in current. It is given by charging and discharging. In a transient response, such as when a circuit is switched on or off, the inductor gradually ramps up or down the current flow. During this process, it stores or releases energy over time. 5. Applications of energy storage. Power supplies. In switch-mode power supplies, inductors store energy during one part of the cycle and release it during another, helping to smooth out fluctuations in voltage and current. Energy storage systems. Inductors are used in various energy storage systems, such as energy harvesting devices and power conditioning circuits. Filtering and tuning. Inductors store energy to filter out unwanted frequencies in signal processing and to tune circuits to specific frequencies. 6. Key considerations. Inductor design. The design of an inductor, including the core material, coil geometry, and number of turns, affects its ability to store energy. Ferrite cores, for example, enhance inductance and energy storage capabilities. Energy density. The energy density of an inductor depends on the core material and design. Higher inductance and current result in more stored energy, but this also requires careful consideration of core saturation and thermal management. In summary, energy storage in an inductor is achieved through the creation of a magnetic field when current flows through the coil. The amount of energy stored is proportional to the square of the current and the inductance of the inductor. This stored energy is crucial for many electronic applications, including power supplies, filtering, and energy management systems. Reduced losses in inductors, particularly those with ferrite cores, refer to minimizing the energy losses associated with the inductor's operation. These losses can significantly impact the efficiency and performance of electronic circuits. Here's how reduced losses are achieved and why it's important. 1. Types of losses in inductors. A. Core losses. Hysteresis loss. Description. Hysteresis loss occurs due to the lag between the changes in the magnetic field and the magnetization of the core material. As the magnetic field reverses direction, some energy is lost as heat due to the core material's inability to perfectly follow the field changes. Impact of ferrite cores. Ferrite materials are chosen for their low hysteresis loss. Ferrite cores have low coercivity, meaning they require less energy to demagnetize and remagnetize, resulting in lower hysteresis losses. Eddy current loss. Description. Eddy currents are circulating currents induced within the core material by the changing magnetic field. These currents create resistive losses, heat, and reduce the efficiency of the inductor. Impact of ferrite cores. Ferrite materials have high electrical resistivity, which helps to minimize the formation of eddy currents. Ferrite cores are typically designed with a granular or powdered structure, which further reduces eddy current losses by increasing electrical resistance. B. Copper losses. Resistance loss. Description. Copper losses occur due to the resistance of the wire windings in the inductor. When current flows through the wire, it encounters resistance, resulting in heat dissipation. Minimizing resistance. Using wire with a larger cross-sectional area or higher conductivity, e.g., copper with a high purity, helps to reduce copper losses. Proper winding techniques and minimizing wire resistance also contribute to reduced losses. 2. Advantages of ferrite cores in reducing losses. A. High magnetic permeability. Efficiency. Ferrite cores have high magnetic permeability, which allows them to concentrate the magnetic flux more effectively. This results in higher inductance and improved efficiency because the core can store and transfer more energy with less magnetic field leakage. B. High electrical resistivity. Reduced eddy currents. The high electrical resistivity of ferrite cores reduces the formation of eddy currents, which decreases energy losses and heat generation. This is especially important in high-frequency applications where eddy currents can become significant. 3. Design considerations to reduce losses. A. Core material selection. Ferrite versus air cores. Ferrite cores are chosen over air cores for applications requiring high inductance and low losses, especially at high frequencies. For lower frequencies or applications where losses are less critical, air cores might be used to avoid correlated losses. B. Core geometry and construction. Shape and configuration. The shape and construction of the ferrite core, e.g., toroidal, E-core, affect magnetic flux concentration and loss reduction. Toroidal cores are often used for their efficiency in containing the magnetic field and minimizing flux leakage. C. Winding techniques. Wire quality. Using high-quality wire with minimal resistance and optimizing winding techniques, e.g., tightly wound coils, helps reduce copper losses and improve overall efficiency. 4. Impact on performance. A. Improved efficiency. Energy conservation. Reduced losses lead to better conservation of energy within the inductor, making it more efficient in storing and transferring energy. B. Thermal management. Heat reduction. Lower losses result in less heat generation, which helps in managing thermal conditions and prevents overheating of the inductor and surrounding components. C. Enhanced circuit performance. Stable operation. Reduced losses contribute to more stable and reliable circuit performance, particularly in high-frequency and power supply applications where efficiency is critical. In summary, reduced losses in inductors are achieved through careful selection of core materials, like ferrite, minimizing core and copper losses, and optimizing design and construction. This results in higher efficiency, better performance, and improved reliability of electronic circuits. Ferrite core inductors are widely used in various applications due to their ability to handle high frequencies efficiently and their effectiveness in reducing losses. Here are some key applications. 1. Power supplies. A. Switch mode power supplies, SMPS. Role. Ferrite core inductors are used in SMPS to filter and regulate voltage. They store energy during one part of the switching cycle and release it during another, helping to smooth out voltage fluctuations and reduce ripple. Benefit. High-frequency operation and reduced energy losses make ferrite core inductors ideal for efficient power conversion and regulation. B. DC-DC converters. Role. In DC-DC converters, ferrite core inductors are used to transfer energy between different voltage levels. They help in maintaining a stable output voltage by smoothing out the fluctuations in the input voltage. Benefit. They improve the efficiency of the conversion process by minimizing losses and handling high switching frequencies. 2. Radio frequency, RF, applications. A. RF filters. Role. Ferrite core inductors are used in RF filters to block unwanted frequencies and allow desired frequencies to pass. They are crucial in tuning circuits to select specific frequencies and reject interference. Benefit. The high-frequency handling capability of ferrite cores ensures effective filtering and minimal signal loss. B. Antenna matching networks. Role. In antenna systems, ferrite core inductors are used in matching networks to match the impedance of the antenna with the transmission line or receiver. This ensures efficient power transfer and minimizes signal reflection. Benefit. Ferrite cores improve the performance of matching networks by providing stable inductance at RF frequencies. 3. Electromagnetic interference, EMI, suppression. A. Ferrite beads. Role. Ferrite beads are small ferrite core inductors used to suppress high-frequency noise and EMI in electronic circuits and cables. They are placed around wires or integrated into circuit boards to filter out unwanted noise. Benefit. They provide effective suppression of EMI, improving signal integrity and reducing interference in sensitive electronics. B. Common mode chokes. Role. Common mode chokes with ferrite cores are used to filter common mode noise in power lines and signal lines. They allow differential signals to pass while blocking common mode noise. Benefit. Ferrite cores enhance the performance of chokes in filtering and reducing noise. 4. Signal processing. A. Tuning circuits. Role. Ferrite core inductors are used in tuning circuits to adjust the frequency response of filters and oscillators. They help in selecting or tuning specific frequencies in communication systems. Benefit. Ferrite cores provide precise inductance values and stable performance, improving the accuracy of tuning circuits. B. Oscillators. Role. In oscillators, ferrite core inductors are used as part of the resonance circuit to generate stable oscillations at specific frequencies. Benefit. They ensure stable frequency generation and minimize drift, which is crucial for reliable oscillator performance. 5. Energy storage. A. Energy harvesting. Role. Ferrite core inductors are used in energy harvesting systems to capture and store energy from environmental sources, such as vibrations or electromagnetic waves. Benefit. Their high efficiency and ability to handle high frequencies make them suitable for converting and storing small amounts of energy. B. Pulse transformers. Role. Ferrite core inductors are used in pulse transformers to convert and isolate high-frequency pulses. They are used in applications such as switching power supplies and pulse circuits. Benefit. Ferrite cores enhance the performance of pulse transformers by improving efficiency and reducing losses. 6. Power management. A. Energy storage systems. Role. Ferrite core inductors are used in energy storage systems to manage and stabilize energy storage and transfer, such as in rechargeable battery systems and capacitors. Benefit: they help in smoothing out energy fluctuations and improving overall efficiency. In summary, ferrite core inductors are versatile components used across a wide range of applications, from power supplies and RF circuits to EMI suppression and signal processing. Their high-frequency handling capability, reduced losses, and efficiency make them crucial in modern electronic and electrical systems. Ferrite core inductors are crucial in modern electronics for their ability to handle high-frequency signals with minimal losses, making them indispensable in telecommunications, computing, and power management systems.